Okay, thanks everyone for joining in for today's TCS Plus seminar. We are very excited to have Julia Chuzoy speaking at the seminar today. Julia is an Manuel Blum professor at TTIC and a part-time professor in Department of Computer Science at U Chicago. She has conducted influential research in various TCS Plus fields, including graph algorithms, hardness of approximations, and structural graph theory. And today we'll be hearing about faster combinatorial algorithms for bipartite matching. Thank you, Julia.
Yeah, thank you, Samega, and thanks for inviting me. So this talk is about faster combinatorial algorithms for bipartite matching, and this is based on joint work with Sanjeev Khanna. So probably all of you are familiar with bipartite matching problem. So we're given a bipartite graph, and what we want to do is to find a matching of maximum cardinality. So here, for example, is a matching of cardinality 3. And probably, as all of you know, one way to solve this problem is to cast it as maximum ST flow. So to do this, we direct all edges from left to right. We add a source that connects to everybody on the left, and we add a destination to which everybody on the right is connected, and then we set all edge capacities to 1. So any integral flow in this flow network defines the matching of the same cardinality as the value of the flow and vice versa. So obviously, if you have any algorithm for maximum flow, you can use it to solve bipartite matching. This is a really well-known fact. A little bit less well-known fact is that there is actually a reduction in the other direction. If you have an algorithm for bipartite matching, you can actually use it to solve maximum ST flow in directed graphs with unit vertex capacities. But in any case, it's the first direction that's important for us. So we can use any max flow algorithm to solve the problem. For example, we can do Ford-Fulkerson. So to remind you, we start with an empty matching, and then we do iterations. And in every iteration, we make this matching bigger. So what happens in every iteration? We start with a current matching. This matching defines flow in this flow network. We compute residual flow network. In the residual flow network, we compute any ST path. It's called augmenting path. And then we augment the flow and the matching along this path, and we get a bigger matching. And it's easy to see that this algorithm can be implemented to run in time of mn, because there is going to be at most n of these augmentations, at most n iterations. And every iteration can be implemented to run in time of O of m. So in 1973, Hopcroft and Karp observed that you can implement similar idea to make it run faster. And the idea is that instead of doing these augmentations one by one, you can do them in bulk. So what they do is they compute a maximal collection of disjoint shortest augmenting paths in the residual flow network, and then they augment the whole flow and the whole matching simultaneously along all of these paths. And this leads to an algorithm whose running time is m square root n. And pretty much this is it. This is what things stood for a very long time. Except that it was noticed that you can actually also solve this problem by using fast matrix multiplication. So this will give you an algorithm with its running time, which is faster than Hopcroft-Karp if your graph is sufficiently dense. So these are the results so far. I'm listing them here. I'm listing all of them under combinatorial algorithms, even though matrix multiplication, you may not count it as a combinatorial algorithm, but let's be generous. And quite recently, a new paradigm emerged that completely revolutionized this whole field. And this paradigm is the use of continuous techniques, and in particular, interior point methods in order to solve flow and other related problems. So this has led to a long sequence of really remarkable results. Several ones of them are breakthroughs in their own right, and probably I'm missing some of them on this list here. And recently, this culminated with this really amazing, almost linear time algorithm for directed maximum ST flow. In fact, even for the more general min cost flow, and it also gives an algorithm with the same running time for bipartite matching. So what is common to all of these works is that all of them are based on continuous techniques, where you take a problem, you cast it as a linear program, and then you use interior point methods to solve it. So to summarize, if we now use these continuous techniques, there is almost linear time algorithm for bipartite matching. But if we stick to the old school combinatorial techniques, then the best current algorithm is still algorithm from 1973, Hopcroft-Karp, with m square root n running time, But for very dense graphs, you can get a little bit faster with fast matrix multiplication. So the question is, are these continuous techniques really essential? Or can we get fast combinatorial algorithms? So of course, the notion of combinatorial techniques is not very well defined, but we sort of intuitively know what it is. And you may wonder, why do we even care? We already have these really great continuous methods. Why do we care to get combinatorial algorithms? So let me give you a little bit of motivation. So first of all, combinatorial algorithms tend to be more transparent and intuitive. For example, we all know that you can solve Max Flow through linear programming. You cast it as an LP, and then you feed it to LP solver. But when we teach Max Flow in class, this is not how we do it. We usually teach Ford-Fulkerson or other combinatorial algorithms. So why we do it? Because these algorithms really, you can see how this flow is gradually constructed. And also they help us introduce really important notions such as residual flow network, augmenting path, and so on, which are really important beyond this problem. Second, these are really basic problems. So getting good algorithms for them can help us discover structures and tools that can be useful in other problems where we don't know how to use continuous techniques. And here, one motivating example is maximum matching in general graphs. So it's a much more difficult problem. And this problem has exact LP, but that LP has exponential size. And right now, we don't have any method how to apply continuous techniques to this problem. So currently, all algorithms use combinatorial algorithms and augmenting path approach. So if we want to get faster algorithms for this problem, it looks like we should first get good combinatorial algorithms for bipartite matching, which is much easier. And lastly, flows, matchings, and all these problems, they're really basic, and they arise in all kinds of settings and need to be solved in all kinds of settings, not just the standard classical one, but also in dynamic, online, distributed, and so on. And in some of these settings, it can be more challenging to adapt the continuous techniques, while combinatorial techniques often just fit in naturally. So with this motivation in mind, we ask again this question: can we get faster combinatorial algorithms for bipartite matching? And in today's talk, we'll see that the answer is yes. And the answer is based on two papers, both of them co-authored with Sanjeev Khanna. The first paper just appeared in SODA, and it's a deterministic algorithm whose running time is m to the 1/3 times n to the 5/3. So this already beats both Hopcroft, Karp, and matrix multiplication-based algorithms on graphs that are moderately dense. The second result that is about to appear in stock, it's a randomized algorithm, and its running time is close to n². So this is close to the best you can hope for in dense graphs, but in sparse graphs, there is still room for improvement. And as I said, this automatically gives an algorithm for directed maximum ST flow with unit vertex capacities with exactly the same running time. So most of the talk today, I'll talk about the first result, which is actually like surprisingly simple. You just need a couple of observations and then just tweaking existing techniques. The second one is a little more technical, and in the end, I'll just say a few words about it, but mostly I'll be talking about the first result. So let me first start with a very high-level overview of the algorithm, and it follows really standard path. So we just start with a matching that's empty. And then we're going to grow it iteration by iteration over the course of polylog n iterations. And we do it until the matching becomes pretty large, pretty close to the optimal one. And at this point, we switch to Ford and Fulkerson, and we do a few more iterations of Ford-Fulkerson to push it all the way to the optimal one. And we'll see in a minute why we do this. So in order to do this, there is this main subroutine. So the main subroutine starts with the current matching M. And throughout, I'm going to denote by delta the distance of the current matching M from the optimal solution value, how much more we need to go. And what we want to do, we want to output a matching that is significantly bigger. The cardinality should be the cardinality of M plus delta divided polylog n. And in the end, this is going to be the running time of this algorithm. So as you can see, after polylog n iterations will be surely finished. And as long as this delta is large, the running time of this algorithm is pretty fast. When delta becomes small, the running time is no longer fast, but at this point, we're pretty close to the optimal solution. So we can just switch to Ford-Fulkerson and run delta more iterations of this algorithm to get all the way to optimal one. So by balancing when exactly we switch from one algorithm to another, this is the running time we get in the end, which is the result of the soda paper. So now I'm going to look into this main subroutine in a little bit more detail. So we start with the current matching M. And as we said, this matching naturally defines a flow in the corresponding flow network. So here, every red edge carries 1 flow unit and every blue edge carries 0 flow units. And next, we compute the residual flow network. And in this kind of a network with this kind of a flow, computing residual flow network simply means we just reverse the directions of the red edges like this. This is the residual flow network. And what we know, what always holds in any residual flow network, it always contains a flow whose value is the optimal flow value minus the current flow value. And for us, this means that in this residual flow network, there are delta disjoint ST paths. So what we want to do, we want to recover a lot of these disjoint paths. Not all the way to delta, but we want delta over polylog n disjoint ST paths. And once we get them, we can augment the matching M through this path, and we get a much bigger matching like we wanted, and we're happy. So what I'm saying here is basically that if you want to solve max flow in directed graphs exactly, it's enough to solve it approximately. This is really well known. There is nothing new here. So the main question is, how do we do this efficiently? So to summarize, so far, what we are saying, it's enough for us to do the following. We have this residual flow network. We know it has delta disjoint ST paths. We want to find delta over polylog n disjoint ST paths. So before I continue to how exactly we do this, I just want to mention a few properties of this residual flow network. So let's delete S and T from this graph. And what we get is bipartite graph. The matching edges are the red edges, and they go from right to left. So obviously, every vertex is incident to at most one right to left edge. The non-matching edges are left to right edges. And yeah. So graphs that have the special property, we're going to work with them quite a bit, and I'm going to call them well-structured graphs. So what's a well-structured graph? It's a directed graph that's bipartite, and every vertex is incident to at most one right to left edge. So these right to left edges, the red edges, I'm going to call them special because they have this extra special property, and the left to right edges, I'm going to call them regular. They don't have this property. And so as I said, we'll work quite a bit with these well-structured graphs. And it looks like this is a very restricted special case of directed graphs. But in fact, there is a really simple transformation that can take any directed graph and transform it into a well-structured graph. It's really simple. I just don't have time to go into this. But the way to think about this is that a well-structured graph is just a convenient representation of any directed graph. In any case, going back, this graph that we get from the residual flow network, it already automatically has this property. So every vertex has either integrate most one or outintegrate most one in this graph. And if we go to the original residual graph, residual flow network, what this means is this. If we get any collection of ST paths that don't share any edges in this residual flow network, they also don't share any vertices except for S and T. Or in other words, edge congestion, vertex congestion, they're the same for this residual flow network. So now going back to our goal, so remember, we know that there are delta disjoint ST paths in this residual flow network. We want to find delta over polylog n such disjoint ST paths. And again, intuitively, this is just saying solve max ST flow problem approximately. So I'm going to define a little bit more general problem. It's called route and cut problem that will be sufficient in order to solve this one, but we'll also use it in other contexts. But intuitively, it's also just approximate ST flow. So let me now define this route and cut problem. So the input is a well-structured graph G and two sets A and B of its vertices. And intuitively, we want to connect vertices of A to vertices of B with a lot of paths. So remember, well-structured graph, it already has this bipartition of its vertices into two subsets. So I just want to mention that A and B, they have nothing to do with the subsets. So any vertex can be in A or in B. And additionally, we have this target parameter delta, which means I want delta disjoint A to B paths. So the output must be a collection of disjoint paths connecting vertices of A to vertices of B, and they need to be completely disjoint. They can't share endpoints, inner vertices, nothing. And if I manage to get delta over polylog n such paths, then this is it and I'm happy. But if not, we want the algorithm to produce a certificate that such a collection of paths does not exist. And the certificate is naturally simply a cut. It needs to separate many vertices of A from many vertices of B, and it should have few edges coming out of it. So this is the problem definition. Again, at a very high level, this is just approximate maximum A to B flow. Now going back to what we wanted to solve. So let me denote by A all the vertices on the left that have an edge coming into them from S. So these are the vertices that are circled in green. And B is going to be all the vertices on the right that have an edge connecting them to T. So these are vertices that are circled in purple. And our goal is simply the same as saying compute delta over polylog n, disjoint A to B path in this resulting bipartite graph. So this is exactly the route and cut problem. Now, in route and cut problem, sometimes if this large collection of paths does not exist, we'll get a small cut that separates many vertices of A from many vertices of B. But in our case, we know that such a large collection of paths does exist. So in our case, we'll never get the cut. We'll always get a really large routing. So if we can solve this route and cut problem, then we can solve the original problem as well. So all we need to do now is just to get a fast algorithm for the route and cut problem. So again, intuitively, what's this route and cut problem? It just, we want a fast algorithm for approximate matching, for approximate flow, sorry. And if you want a fast algorithm for approximate flow, there is a really neat tool that allows us to find it, and it's called multiplicative weight update framework. So before I describe this algorithm, let me first describe the LPs, and these are going to be the standard flow LP and its dual. So I'm going to denote by capital.
I have a question.
Yes.
I guess, yeah. So as I'm not well aware of the exact running times. So when you say that for the route and cut problem, we want a fast algorithm, like what is the base runtime of basing algorithm and what is
Okay, so this is an approximate flow problem, right? Yeah. So whatever is known for maximum flow in directed graphs, this is what's known for this problem. Right now, we just want to beat m square root n algorithm of Hopcroft Karp for this problem.
For this problem, okay.
Yes. Okay, so now I'm going to just define the flow LP and its dual, and then they will help us guide the algorithm and the analysis. We're actually not going to solve these LPs. So I'm going to denote by capital P the set of all A to B paths. And for each such path, there's going to be a variable f of P that we can think of as the flow on this path. And then this is a completely standard flow LP. We want to send maximum amount of flow between these vertices from A to B. And the constraint is that for every edge, the total flow on this edge is at most 1. So standard flow LP. And now we compute its dual, and it's also completely standard LP. It's actually a relaxation of min cut. So for every edge, there's going to be a variable L of E, and I'll think of it as the length of this edge. And then intuitively, what does this dual says? It says assign lengths to the edges so that the length of every A to B path becomes at least 1. And subject to this, minimize the total length of all the edges. So these are the two LPs. Now let's see the multiplicative weight update algorithm. So initially, we assign a tiny length to every edge. So this capital N, it should just be sufficiently large. For example, M over delta is big enough. And then we do iterations, and we do iterations as long as there is an A to B path whose length is at most 1. And then in every iteration, I take any such path. I send one flow unit on this path, and I double the length of every edge on this path. And this is it, that's the whole algorithm. So now why does it work so well? So in every iteration, the flow grows by 1. The dual solution cost, which is the total length of all the edges, grows by at most 1. Why? Because I take a path whose length is at most 1, and I double the length of every edge on this path. And in the end, we get a feasible dual solution because the length of every A to B path becomes at least 1. And we also get a flow whose value is at least as large as the value of this dual solution, which means we get an almost optimal flow. Now, if we look at some edge, I claim that we're going to use this edge at most log n times. And the reason is that every time I use this edge, I double its length. And once the length of the edge reaches 1, I cannot use it anymore because we only use paths of length at most 1. So what we get is close to optimal flow, but with logarithmic congestion. This is not quite what we wanted. What we wanted was integral flow with no congestion. It turns out once you reach this point, it's really easy to take this flow and to recover from this delta over poly log n disjoint A to B path. So I will not go into this. It's really simple, and it's also a fast algorithm that allows us to do it. So whatever we get here, almost optimal flow with logarithmic congestion is just going to be good enough. So now the whole problem simply boils down to implementing this algorithm efficiently. And if you look at this algorithm, there is only one non-trivial part here. It's how we compute a short A to B path in every iteration. And you may say, well, it's simple. We know there are good algorithms, efficient algorithms to compute shortest path in a graph, right? But the thing is, if we compute such a path from scratch in every iteration, it will take time of m. And you cannot do it faster if you do it from scratch. And the number of iterations delta can be as large as n. So this will give us running time n times m, and it will not allow us to beat Hopcroft Karp, which is m square root n. So our hope is that we don't really need to compute this path from scratch in every iteration because we are working with roughly the same graph. It just changes a little bit. So we hope we can maintain some additional data structure that will allow us to report this path faster. So what we need is an algorithm that does exactly this, that in every iteration will give me a short A to B path if it exists. And I'm going to call this algorithm an oracle. So what we want is a fast oracle. So there is now a good news and a bad news. So the good news is that this oracle can actually be reduced to a problem that is very important and that has been studied a lot. And this problem is the incremental single shortest path in directed graphs. The bad news is that we don't have really good algorithms for this problem. And here I want to emphasize, if the graph was undirected, then this problem does have good algorithms. But because we need to work with directed graphs, we don't really have good algorithms for this problem. So what do we do? How do we get around it? So the main insight from our SODA paper is that we can slightly modify this multiplicative weight update algorithm so that we get a special case of decremental single source shortest path that seems easier. And then our main technical contribution, we just take existing algorithm for decremental single source shortest path, we tweak it so that in this special case, it becomes faster. And I can tell you right away how we modify this multiplicative weight update algorithm. And so currently, so this algorithm says it's allowed to terminate once the length of every A to B path becomes at least 1. So what we observe is that it's actually okay to terminate the algorithm earlier. If somehow we discover that the largest number of disjoint A to B paths that are short becomes sufficiently small under delta over poly log n, we can stop. And short here is 1/8. So even if we stop early because we discover that this condition holds, everything still works and we still get almost optimal flow like we wanted. So from now on, we'll just focus on designing an algorithm for this oracle. And just to make things easier, I'm going to add a source that connects to everybody in A and a destination to which everybody in B connects. And this is just so that I can talk about ST paths instead of A to B paths. And also I'm going to scale all edge lengths by factor n. So at the beginning, all edge lengths are 1. And then as the algorithm progresses, they grow, but they remain integral. It's just easier this way. So in a nutshell, what do we want this oracle to do? So the oracle is given a graph, and this graph undergoes edge length increases. And then in every iteration, we want this oracle to return a short S to T path if it exists. And I'm going to say that when it returns such a path, it responds to a query. So the query is, give me a short ST path. And we're allowed to stop the algorithm early if we somehow figure out that the largest number of disjoint ST paths that are short that remains in the graph becomes small. And we want the total running time of this oracle to be short. And the running time includes both the time to maintain the data structure and the time to respond to all the queries or to report all the paths. So I said it can be viewed as an instance of decremental single socialist path. So let me tell you what is this problem. So it's very similar, but now the graph undergoes edge deletions, not edge length increases. And it's more general. So you can ask queries between S and any other vertex. And given such a query, the algorithm needs to return shortest or approximate shortest path between them. The number of queries can be anything. And typically what we want is that the time that is required to respond to a query should be at most roughly the number of edges on the path. So this is very similar to what we need to solve, but not quite, because our graph, it undergoes edge length increases. Here, the graph only undergoes edge deletions. But it turns out it's not a problem at all. It's easy to implement edge length increases as edge deletions by a very simple trick, and this is also well known. So let me show you how. So for every edge in my original graph, I'm going to replace it with log n parallel edges whose lengths are 1, 2, 4, and so on, all the way to capital N, all of them powers of 2. And now whenever the length of this edge doubles, I'm simply going to delete its shortest copy. And this is how I'm going to implement edge length increases by edge deletions. So in other words, this problem that we need to solve here, this oracle, can be solved by a decremental single socialist path. So let me now tell you what is known for this decremental single socialist path. And I want to emphasize two things. First of all that I'm going to say here is for directed graphs. For undirected graphs, there are better algorithms. And second, I will only talk here about adaptive adversary setting, because this is what we need. If you don't know what it is, it's not important. But if you know what it is, then there are better algorithms for oblivious adversary. But we focus on adaptive one. So if your graph is a DAG, directed acyclic graph, then there is a pretty good approximation algorithm. It achieves running time close to n squared. But in general graphs, this is the best current running time, roughly n to the 8/3. And this is just too slow for us. If we just take this algorithm and we plug it into this whole scheme, we will not beat Hopcroft Karp. So our main insight is that we don't really need to solve this whole problem. We need to solve a restricted special case that has a lot of extra features that can make it easier. So let me tell you what are these features. So first of all queries are between a fixed pair of vertices S and T. And the number of queries is not too large. It's at most delta. Second, and this seems to be a really important one that actually gives us an edge, is that we only need to respond to queries as long as there are many disjoint and short ST paths. Also, the edge deletions, they're not really completely crazy, right? Edges are only deleted when they lie on the paths that our algorithm returned in response to queries. So they're somehow a little controlled. And also, we only care about the total time it takes to respond to all the queries. If some query takes more time and some other query takes less time, that's fine by us. So we exploit all of these properties and we modify this previous algorithm of Bernstein, Gutenberg, and Saranurak to get a faster algorithm for this special case of decremental single socialist path that we need to solve. So now I'm going to tell you a little bit about this algorithm of Bernstein, Gutenberg, and Saranurak and how we modify it to make it faster for our special case. So the algorithm can be thought of as consisting of two big parts. And the first part, it maintains a decomposition of the graph into expander-like subgraphs, which I'm going to call clusters. And this algorithm also supports short path queries between pairs of vertices inside each cluster. So if you give it two such vertices, it will return a short path connecting them. And another important feature of this algorithm is that if we take our original graph and we contract every cluster into a single vertex, then this contracted graph, it looks almost like a DAG. And why this is useful? Because there are good algorithms for single sorted paths on DAGs. And we can hope to apply these algorithms to this contracted graph, which is an almost DAG, and get a good running time. So the second part is exactly this. It's applying a known algorithm for decremental single sorted paths on almost DAGs to this contracted graph. So now I'm going to switch to the second part, and later I'll come back to this expander decomposition part. So first of all, what's a DAG? A DAG is a directed acyclic graph. So it's a directed graph that has no cycles. In other words, I can order its vertices from left to right so that all edges are directed from left to right. What's an almost DAG? In an almost DAG, we allow some right to left edges. And I'm going to say that the span of this edge is the distance between its endpoints in this ordering. So this is how many vertices lie between the endpoints of this edge plus 1. In this case, the span is 3. And intuitively, what's an almost DAG? It's a graph for which you can find an ordering of its vertices so that the total span of all right to left edges is quite small. There is this really cool algorithm of Bernstein, Gutenberg, and Wolff-Nielsen that generalizes their algorithm for decremental single sorted paths on DAGs to almost DAGs. And what they show is that if the total span of all right to left edges is gamma, then the running time of their algorithm is n squared plus gamma times n. So when gamma is small, it gets faster. Now, if we look at the general single sorted path problem, even if the query is just between S and T, it's possible that the shortest or all almost shortest ST paths, they use a lot of these right to left edges. Maybe they use all of them. But for us, we only need to respond to queries as long as there are a lot of short and disjoint ST paths. And these right to left edges, they need to be distributed among these short ST paths. So there's always going to be at least one short ST path for which the total span of its right to left edges is not that large. It's at most gamma over delta. And this is what really gives us the edge. We just show that in this special case, the same algorithm can be improved to run in time n squared plus gamma n over delta. And this is how we get this faster algorithm when this delta is large. So this is all I wanted to say about the second part. Mostly it's just observing that this algorithm is faster for this special case. And now I'm going to switch to the first part, the expander decomposition part, which is the more technical one. So first, a few words about cuts in directed graphs. So cut is, as usual, a partition of vertices into two subsets, x and y. But I'm going to distinguish between xy and yx. So the order is going to be important. And these are directed graphs, so we have edges in both directions. And remember that we work with well-structured graphs. So we have these red special edges, and every vertex is incident to at most one of them. And the rest of the edges are blue edges. They are regular, and a vertex can be incident to many of them. So for well-structured graphs, I'll require that all edges that go from x to y, they have to be special ones. And then I say, that a cut is phi sparse if the number of these red edges going from x to y is at most phi times the number of vertices on the smaller side. And then, as usual, we say that the graph is a phi expander if it does not contain any cut whose sparsity is less than phi. And just like in undirected graphs, if your graph is a phi expander, then for every pair of vertices, there is a path connecting them of length at most roughly log n divided by phi. And this is a directed graph, so there's going to be a path in one direction and a path in the other direction, which both are going to be short. So now remember that what we want to do, we want to maintain a decomposition of our graph into expander-like clusters. And the main subroutine that we are going to use, I call it here maintain expander. This is a subroutine that's responsible for maintaining a single cluster in the decomposition. And eventually, every cluster that is going to be added to the decomposition, we're going to run this maintain expander subroutine on it. So what is this maintain expander subroutine? So we start with some graph G and some distance parameter D. Now this G is actually going to be one of our clusters in the decomposition. And then this G undergoes edge deletions over time. And at any time, we can get a short path query. So in this query, given a pair of vertices X and Y, we need to return a path connecting X to Y, whose length is at most D, which is this input parameter that we received. And the time that it takes to respond to this query should be roughly bounded by the number of edges on this path. Of course, obviously, it's possible that the diameter of G is just too big and such a path does not exist. Or maybe it existed at the beginning, but we deleted some edges and the diameter became too large and now it doesn't exist. So to make sure we never run into this problem, we allow the algorithm at any time to return a sparse cut. The sparsity is roughly 1 over D. And when it does so, we take the vertices on one of the sides, the smaller one, and we simply delete them from this cluster or this graph. And then the algorithm needs to continue with what is left from this cluster, which is B in this case. So we want to use the subroutine in order to maintain expander decomposition of our graph. So let me show you how we do this. At the beginning, we start with our graph, and we have only one cluster in the decomposition. This cluster is the whole graph. And we apply the maintain expander subroutine on this cluster. And then at some later point, or maybe even immediately, this maintain expander subroutine produces a sparse cut AB in this cluster G. And now, instead of one cluster G, we will have two clusters in our decomposition, B and A. And we order them like this, first B and then A. And the reason we do it like this is that we want to make sure that we have few right to left edges. So the number of these red edges is relatively small because that cut is sparse. And now, one of the sides of this cut, A or B, is deleted from the cluster G. So let's say it's A. So maintain expander on G has to continue with what's left of this G, which is the cluster B. And A is now a new cluster. So we start a new instance of maintain expander, which we run on A. And we keep on going like this. Maybe later we get a sparse cut XY of A. Now we replace A with Y and X, again in this order to ensure that there are few right to left edges. And at all times, we're going to run this maintain expander on each one of the clusters. Now, remember this maintain expander problem, it comes with this distance parameter D. And we can think of this D as the desired bound on the diameter of the cluster. It turns out it's really important how we choose this D, and it's going to be different for different clusters. So on the one hand, we need the total diameter of all the clusters to be small. And the reason is that eventually we simply contract them, and then we compute a short ST path. We need to make sure that they don't contribute too much to the eventual length of the path, which is not allowed to be too large. So we want these Ds to be small. On the other hand, we want the total span of these right to left edges also to be small. And this is to make sure that the algorithm for SSSP on the resulting contracted graph is fast. The number of these right to left edges depends on the sparsity of the cuts, which is roughly 1 over D. So we also want these Ds to be pretty large. So it turns out that the right choice for this parameter D for a cluster X is something like the number of vertices in X divided by delta. And something pretty similar was also used in previous works. But one thing that I want you to notice here is that this parameter D, it may be pretty big. It might even be polynomial in n, for example, square root n. So now when we go back to the maintain expander problem, so let me denote by phi 1 over D. And at a very high level, what is this problem? What does it ask us to do? So we have some graph. It undergoes edge deletions. And we want to maintain this graph as a phi expander. And the only thing that we're allowed to do is cut off sparse cuts off of this graph. And we also need to support some short path queries. So this kind of a problem, it arises a lot. And this problem and its various variations have been studied a lot, mostly in undirected graphs. For directed graphs, this previous result on decremental single associative space gets an algorithm for this problem whose running time is m over phi squared, which for us is md squared. And typically, this is the running time that you get for this problem from previously known algorithms. And typically, this is OK, because normally this d is not very large. It's like polylog n. But in our case, we need it to work even if d is very large. And so because of this, this running time is too slow for us. So again, what we do in our soda paper, we exploit again all the advantages of our settings, and we also choose some parameters really carefully so that in the end, we get an algorithm whose running time is md plus n squared. So I just want to mention, first of all, this algorithm uses completely standard techniques, so like cut matching game and Evans-Shiloh trees. And even because we are willing to afford here n squared running time, we simplify some of these techniques and get really elementary algorithms for some of them. And this running time is sufficient to get our soda algorithm, soda result, to get an algorithm that is faster than Hopcroft-Karp for moderately dense graphs. But this is still too slow for our stock result. And not only is that it's too slow, this running time is only achieved for some very specific choice of parameters. And to get the stock result, we needed to work for a broader range of parameters. So now I'm going to say just a few words about what we do in the stock paper, how we get to the n squared result. So what we notice is that if you get a fast algorithm for route and cut, you can actually use this algorithm to solve maintain expander problem. So this reduction is non-trivial and requires quite a bit of work. But at the end, here is where we stand. We show that if you get fast algorithm for route and cut, then you can get fast algorithm for maintain expander. And there is also reduction in the other direction. This is what you get from multiplicative weight update and SSSP on almost DAGs. This is something we've seen. So this looks completely useless because here are two problems that we want to solve. And we just say, if we have fast algorithm for one of them, we can solve the other. But we don't have a fast algorithm for any one of them. So what do we do? So to get around this issue, we parameterize both problems with the new parameter R. So if we look at the maintain expander problem, it already comes with this distance parameter d, which is the desired bound on the diameter of the expander. And we say that this instances are restricted if this d is bounded by 2 to the r squared log n. If we look at the route and cut problem, if we manage to route delta paths from A to B with no congestion, then it's easy to see that most paths, they cannot be too long. So most of them will have lengths roughly at most n over delta. So I can think of this n over delta as my distance parameter. And again, I can say instances are restricted if the distance parameter is at most 2 to the power of r squared log n. So we show again reductions in both directions, but they are now a little bit subtler. So we show that if you have a fast algorithm for r restricted route and cut, then you can get a fast algorithm for r restricted maintain expander. And in the other direction, it's from r restricted maintain expander to r plus 1 restricted route and cut. And when r is 1, then it's easy to get fast algorithm for both of these problems. This is just a special case where this distance parameter is small. And so in the end, we just do induction on r, and then we get fast algorithms for both of these problems for the whole range of parameters. And I want to say just a few final remarks about the result that we get for route and cut problem. So remember, in this problem, we needed to connect vertices of A to vertices of B with many paths. So in the end, the running time of our algorithm looks like this, n times n minus the cardinality of B. So when the set B contains a lot of the vertices, like almost all vertices of the graph, the algorithm becomes quite fast. And it may even be faster than the time it takes to read all the edges in the graph, to read the whole input. So this is maybe interesting in its own right, but this is also necessary for us. In order to make these reductions go through, we need an algorithm that has this kind of running time. And this is what makes both of these reductions even more challenging. So to summarize, we get two combinatorial algorithms for bipartite matching, which are faster than Hopcroft-Karp and then matrix multiplication-based techniques if your graph is sufficiently dense. The first result that is based on the soda paper, it's a deterministic algorithm. The running time is m to the 1/3 times n to the 5/3. And the main idea is that we reduce to a restricted special case of decremental single socialist path. And then we just modify existing algorithm for this problem to make it run faster for the special case. And the second algorithm that is based on the stock paper, the running time becomes close to n². The algorithm is randomized. The very high-level ideas are similar, but it's more technical and you need more ideas. And finally, open problems. The obvious open problem is that we want to get an algorithm for bipartite matching, which is combinatorial, but the running time is almost linear. So it matches what we have for continuous techniques. Second question, can we get fast combinatorial algorithms for the more general max flow with general edge capacities? So this was on my list of open questions, but just recently I learned that there is this new result of Bernstein, Blikstad, and Saranurak that actually gets an n² time algorithm for exactly this problem, max flow with general edge capacities. So we can now move the goalpost further and ask, can we do the same for min cost flow, which is more general? And lastly, a really interesting open question is breaking this long-standing m times √n running time for general matching. And can the techniques that we introduce here help with that? And that's all. Thank you.
Thanks, Julia, for the great talk. Let me stop the recording so that we can ask questions freely.